PS 5% is generally the maximum voltage drop allowance for electrical systems, including residential buildings and commercial buildings. This means that the voltage at the end of a circuit should not be more than 5% less than the voltage at the beginning of the circuit. For a 100 amp subpanel located 200 feet from a 200 amp house main, using number 2 American wire gauge wire is acceptable according to the National Electrical Code. The NEC Table 310.15b16 shows that number 2 American wire gauge copper wire is rated for 110 amps at 75 degrees Celsius, which is the standard temperature rating for residential and commercial buildings. To calculate the voltage drop, we can use the following formula: voltage drop equals load current multiplied by circuit length multiplied by resistance per foot. For number 2 American wire gauge copper wire, the resistance per foot is 0.51 ohms. Plugging in the values, we get voltage drop equals 100 amps multiplied by 200 feet multiplied by 0.51 ohms, which equals 10.2 volts. This voltage drop is less than the maximum allowable voltage drop of 5%, which is calculated as follows: maximum voltage drop equals line voltage multiplied by 5%, which equals 120 volts multiplied by 0.5, which equals 6 volts. Therefore, using number 2 American wire gauge wire for a 100 amp subpanel located 200 feet from a 200 amp house main is acceptable according to the NEC and will result in a voltage drop that is within the allowable limit. Now let's delve into the concepts of voltage drop and wire sizing in more detail. Understanding these principles is crucial for ensuring safe and efficient electrical installations. Voltage drop refers to the decrease in voltage that occurs along a conductor as electrical current flows through it. This drop is primarily caused by the resistance of the wire. The longer the wire and the higher the current, the greater the voltage drop. Excessive voltage drop can lead to several problems, including dimming lights, malfunctioning appliances, and overheating of electrical components. Therefore, it is essential to minimize voltage drop to maintain proper system performance. The National Electrical Code, commonly referred to as the NEC, provides guidelines for electrical installations in the United States. It is a comprehensive set of standards designed to ensure the safety of people and property. The NEC addresses various aspects of electrical systems, including wiring methods, overcurrent protection, grounding, and voltage drop. The NEC recommends limiting voltage drop to a maximum of 5% for branch circuits and feeders. A branch circuit is the portion of an electrical system that extends from the final overcurrent device protecting the circuit to the outlets. A feeder is the circuit conductors between the service equipment or the source of a separately derived system and the final branch circuit overcurrent device. The 5% limit is a general guideline. Some specific applications may require even lower voltage drops. To calculate voltage drop, you need to consider several factors, including the load current, the circuit length, and the resistance of the wire. The load current is the amount of current that the electrical devices connected to the circuit will draw. The circuit length is the total distance that the wire travels from the source to the load and back. The resistance of the wire depends on its material, size, and temperature. Copper and aluminum are the most common materials used for electrical wiring. Copper has a lower resistance than aluminum, so it is generally preferred for applications where voltage drop is a concern. The size of the wire is measured in American wire gauge or AWG. Smaller AWG numbers indicate larger wires. Larger wires have low resistance, which reduces voltage drop. The temperature of the wire also affects its resistance. As the temperature increases, the resistance also increases. The formula for calculating voltage drop is voltage drop equals current, often measured in amps, multiplied by resistance, often measured in ohms. However, since wire resistance is typically given in ohms per foot, you also need to multiply by the circuit length. So, the complete formula is voltage drop equals current multiplied by resistance per foot multiplied by circuit length. For alternating current circuits, such as those found in homes and businesses, you may also need to consider the power factor of the load. The power factor is a measure of how effectively the electrical power is being used. A power factor of 1 indicates that all of the power is being used to do work, while a power factor less than 1 indicates that some of the power is being wasted. To account for the power factor, you need to multiply the voltage drop by the power factor. The NEC provides tables that list the resistance per foot for different sizes and types of wire. These tables are typically found in Chapter 9 of the NEC. You can use these tables to determine the resistance per foot for the wire you are using. Once you have calculated the voltage drop, you can compare it to the maximum allowable voltage drop to determine if the wire size is adequate. If the calculated voltage drop exceeds the maximum allowable voltage drop, you will need to increase the wire size or shorten the circuit length. In the example provided, the voltage drop for a 100 amp subpanel located 200 feet from a 200 amp house main using number 2 American wire gauge copper wire was calculated to be 10.2 volts. This is greater than the maximum allowable voltage drop of 6 volts, which is 5% of 120 volts. Therefore, number 2 American wire gauge wire is not adequate for this application. To reduce the voltage drop, you could use a larger wire size such as number 1 American wire gauge or number 1/0 American wire gauge. Alternatively, you could shorten the circuit length by moving the subpanel closer to the main panel. When selecting wire size, it is also important to consider the ampacity of the wire. Ampacity is the maximum amount of current that a wire can safely carry. The NEC provides tables that list the ampacity of different sizes and types of wire. These tables are typically found in NEC Table 310.15b16. The ampacity of the wire must be greater than or equal to the load current. In the example provided, number 2 American wire gauge copper wire has an ampacity of 110 amps at 75 degrees Celsius. This is sufficient for a 100 amp subpanel. However, if the load current were greater than 110 amps, you would need to use a larger wire size. In addition to voltage drop and ampacity, you also need to consider the insulation rating of the wire. The insulation rating is the maximum voltage that the insulation can withstand without breaking down. The insulation rating must be greater than or equal to the voltage of the circuit. Common insulation ratings for residential wiring include 600 volts. When running wire through walls or ceilings, you need to follow the NEC guidelines for wiring methods. The NEC specifies the types of wiring methods that are permitted for different applications. Common wiring methods for residential wiring include non-metallic sheathed cable, commonly known as Romex, and electrical metallic tubing, or EMT. Non-metallic sheathed cable is a type of cable that consists of 2 or more insulated conductors enclosed in a non-metallic jacket. Electrical metallic tubing is a type of rigid metal conduit that is used to protect wires. When installing electrical wiring, it is important to follow all applicable codes and regulations. Electrical work can be dangerous, and it is essential to take precautions to avoid electrical shock. If you are not comfortable working with electricity, it is best to hire a qualified electrician. Here are some additional points to keep in mind when calculating voltage drop. Firstly, remember that the NEC recommends a maximum voltage drop of 5% for branch circuits and feeders. This is a general guideline, and some specific applications may require even lower voltage drops. Secondly, use the correct formula for calculating voltage drop. The formula is voltage drop equals current multiplied by resistance per foot multiplied by circuit length. For alternating current circuits, you may also need to consider the power factor of the load. Thirdly, use the correct values for the variables in the formula. Be sure to use the actual load current, the total circuit length, and the correct resistance per foot for the wire you are using. Fourthly, consult the NEC tables for wire resistance and ampacity. These tables are typically found in Chapter 9 and NEC Table 310.15b16 of the NEC, respectively. Fifthly, consider the temperature rating of the wire. The ampacity of the wire is affected by its temperature. The NEC tables typically list ampacity values for wires at 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. Sixthly, follow the NEC guidelines for wiring methods. The NEC specifies the types of wiring methods that are permitted for different applications. Seventhly, if you are not comfortable working with electricity, hire a qualified electrician. The electrical work can be dangerous, and it is essential to take precautions to avoid electrical shock. Let's consider some examples to further illustrate the concepts of voltage drop and wire sizing. Example 1. A 120-volt branch circuit supplies a 10-amp load located 100 feet from the panel. The wire is number 12 American wire gauge copper. What is the voltage drop? The resistance per foot for number 12 American wire gauge copper wire is 0.1588 ohms. The voltage drop is calculated as follows. Voltage drop equals 10 amps multiplied by 0.1588 ohms per foot multiplied by 200 feet, which is the circuit length, equals 3.176 volts. The percentage voltage drop is calculated as follows. Percentage voltage drop equals 3.176 volts divided by 120 volts multiplied by 100% equals 2.65%. This is less than the maximum allowable voltage drop of 5%, so number 12 American wire gauge wire is adequate for this application. Example 2. A 240-volt feeder supplies a 50-amp load located 200 feet from the service equipment. The wire is number 6 American wire gauge aluminum. What is the voltage drop? The resistance per foot for number 6 American wire gauge aluminum wire is 0.787 ohms. The voltage drop is calculated as follows. Voltage drop equals 50 amps multiplied by 0.787 ohms per foot multiplied by 400 feet, which is the circuit length, equals 15.74 volts. The percentage voltage drop is calculated as follows. Percentage voltage drop equals 15.74 volts divided by 240 volts multiplied by 100% equals 6.56%. This is greater than the maximum allowable voltage drop of 5%, so number 6 American wire gauge aluminum wire is not adequate for this application. To reduce the voltage drop, you could use a larger wire size such as number 4 American wire gauge aluminum. Example 3. A 480-volt feeder supplies a 100-amp load located 300 feet from the service equipment. The wire is number 2/0 American wire gauge copper. The power factor of the load is 0.8. What is the voltage drop? The resistance per foot for number 2/0 American wire gauge copper wire is 0.988 ohms. The voltage drop is calculated as follows. Voltage drop equals 100 amps multiplied by 0.988 ohms per foot multiplied by 600 feet, which is the circuit length, multiplied by 0.8, which is the power factor, equals 4.74 volts. The percentage voltage drop is calculated as follows. Percentage voltage drop equals 4.74 volts divided by 480 volts multiplied by 100% equals 0.99%. This is less than the maximum allowable voltage drop of 5%, so number 2/0 American wire gauge copper wire is adequate for this application. These examples illustrate how to calculate voltage drop and select the appropriate wire size for different applications. By following the NEC guidelines and using the correct formulas, you can ensure that your electrical installations are safe and efficient. Remember to always consult the NEC and other applicable codes and regulations before starting any electrical work. And if you are not comfortable working with electricity, it is best to hire a qualified electrician.